Hello, hello, hello. I can scream if I need to. All right, welcome back from lunch. Hope you're all well caffeinated. I'm sure you're going to want to hear this talk. The man needs no introduction, but he's talking about EIP 4844, what prototype sharding means for the Ethereum ecosystem, how it helps everything scale, how it makes everything lighter, as well as data availability. So for now, I'll pass it over to Vitalik.
Okay, great. So hello, everyone. How have people's mornings been today? Has anyone's morning been available today? The answer should be no. But okay, so let's talk about data being available. So data availability has been this big buzzword in Ethereum land for a couple of years now. And I think it's important to just start off by talking about what it is and why it's important and why things other than blockchains don't provide it. So data availability at the core is a guarantee that some piece of data that's represented by some smaller thing, so it could be represented by a hash, for example, has been published in such a way that gave anyone the chance to download it, right? So the data has been published in such a way that anyone can see that, okay, this particular piece of data went through this process, and as a result of that, we can be sure that whoever wants to download it, or whoever during some long enough historical time span wanted to download it, is or what was actually able to download it. Data availability is not the same thing as a lot of other things, right? So for example, blockchains provide data availability, but IPFS does not, right? And I think it's the best way to understand really what data availability is and is not is to kind of sort out the difference between these two examples, right? So what happens in a blockchain? So let's say, for example, in a blockchain, you download a block. When you've downloaded the block, you download that block and then you republish the block, right? And because you've downloaded the block yourself and you've also republished it again, you know that that block now is available at that particular point in time. And because you have consensus on the block, because you have proof of stake or proof of work or whatever else, then you also know that there is consensus on the facts that that data is available. IPFS does not do this, right? IPFS is a publishing platform. So for example, I use IPFS. So anytime I write a new blog article, if you go to vitalik.eth.limo, because that's the best .eth forwarder these days. I mean, you can do vitalik.eth.link too, maybe, I forget, and then slash something. Then you get an HTML page, and that HTML page is actually stored in the IPFS system, and anyone can go download it, right? But the difference between that and a blockchain is that if you go and download a particular thing off of IPFS, you do not actually have any kind of knowledge that other people were able to see it at any particular point in time, right? So what you always can do is when you download a page from IPFS, you can republish it, and then you know that now that page is available to anyone. But you did not know anything about its availability during any historical point in time, right? Because, maybe that page was never available to anyone all the way right up until the exact second that you received it, right? Maybe you're actually the victim of a very specific type of targeting attack, and it's only showing you the IPFS pages, and if anyone else tries to download them, then they're not going to see anything, and if you download them, then you're going to see them, but you're only going to see the specific. Not like this, right? With a blockchain, if I sync an Ethereum node and I go and check a block from 10 days in the history, I know that it's available, but I also know that it was available 10 days ago, right? So that's the big difference between what a blockchain does and what IPFS does. And it's a really important distinction for a bunch of different applications because it's really crucial for coming to consensus on what happened in the past, right? So if you don't have a data availability system, then what you have this kind of thought experiment that you become vulnerable to, where you imagine you have two possible worlds, right? In world one, you have a bad blog publisher that published a blog where one piece of data is missing. And then you have someone else who tried to download it, they failed, and then they raised an alarm. And then 1 second after the alarm, whoever created the blog just publishes the remaining data. In world two, you have a totally fine blog publisher that just publishes the entire blog, and then you have someone who raises a false alarm. If all you see is just the internet evidence that you see at T3, then you have no way of distinguishing between these two, right? And so the problem is basically, if you do not have some kind of like, quote, dedicated data availability system, then if all that you see is what happens at T3, so you just join the system for the first time at T3, you have no idea who here misbehaved and who here behaved correctly, right? Now, this is particularly important when building certain kinds of scalable like systems, particularly things like rollups, right? And the reason why it matters is because there's a lot of attacks on rollups that you can do that only depend on hiding data. They do not depend on creating invalid data. So if you make an attack on a rollup that depends on creating invalid data, then you can solve that by using techniques like fraud proofs, right? So let's say I publish a blog, and let's say just like take a simple mathematical example, right? Let's say, for example, I want to publish a proof that like some number that is somewhere between 1 million and 2 million is prime. And so what I'm going to do is I am going to just like publish that claim. And then if the claim is wrong, what you can do is you can give me one of the factors, right? You can give me a number like somewhere between like 2 and 2,000. And you can tell me like, hey, this particular number evenly divides this value. And like if you have this particular number, you could just trivially divide and see, wait, that number has a factor, so it's not prime, right? If you look at an Ethereum block, then if I publish an Ethereum block and I tell you it's valid, you can go and tell me like, no, actually it's invalid, and this is the first transaction that you processed incorrectly, right? So this is a technique that's called a fraud proof, but the reason why fraud proofs work is that you have a record of who actually did what, and so you have a record of who did something wrong, and so you know whom to penalize, right? So let's say, for example, I publish an invalid Ethereum block, and then you go and challenge and basically say like, hey, the Ethereum block is wrong over here. And then maybe I need to respond to the challenge and show you like actually it's correct and like here's some Oracle branches. Or maybe I can't do that, right? If the block actually is invalid, then there is evidence that I actually published a block which is invalid, and I even signed the invalid block. I said that the block is valid when actually it's invalid, and then you were the one that went ahead and challenged it. Now, what this means is that the system can penalize me. It can take my money. It can say, you made a bad block. You lose $1 million. And it can take those $1 million, probably burn half of them because that's usually better for security, and then give the other $500,000 to the person who actually who went ahead and challenged the invalid block. With unavailable data, you cannot do this, right? And so if you do something like, if I do something like I publish a block, but I just like hide a bunch of the transactions and I hide the state at the end, and so now nobody can actually calculate like what actually is the result of executing this block, then I haven't actually like stolen money from you, but I possibly froze your money. And the reason why I froze your money is because I did not publish information that you are going to need if you want to ever actually withdraw your coins, right? And so the problem is that in that kind of situation, well, maybe I failed to publish the data, but then, okay, fine, you challenge me. But then when you challenge me, I just respond 1 second later and say, oh, here you go, there's the data. You challenge me again, oh, here you go, there's the data. And basically, there's this problem where if you have to pay for the challenges, then I can just delay publishing and I can just drain your money by making you sign these challenges. Or if I have to pay for responding, then you can just go and make challenges for free and you can grief me, right? And so we have this kind of system where, or this problem where like you can't really make a nice economic game where it actually makes sense to challenge and actually make, and where you actually have this kind of stable outcome around either the data being published or the data not being published. So this is the problem that data availability systems solve, right? So data availability systems try to just create the guarantee for as big blobs of data as possible that this blob actually was published and that it actually was published at this particular point in time. And so anybody at a particular point in time had access to it. Now, the simplest way to make a data availability system is to just have a blockchain, publish a block, and then anyone goes and downloads the block at that particular time. And then for the benefit of people who are offline, and in those cases where you might have a 50-50 split, we have a consensus algorithm, which a blockchain has, and then the system comes to an agreement. Either it agrees that this block was available and it's part of the canonical history, or it agrees that, well, maybe this block was not available, or maybe it was just late. In any case, it's not part of the canonical history, we're ignoring it. If you did something with that block, just try again. Now, we can make systems that provide a similar guarantee, but in a way that is much more scalable, right? And I think the intuition here is basically that, like, if you think about blockchains, and then if you think about actually scalable non-blockchain peer-to-peer systems, like torrent networks, for example, in a torrent network, nobody actually downloads every single file, right? Like, if everybody had to download every single file in a torrent network, it would just be completely crazy, and it would just not actually work. Who here wants to download every single file on the internet? Okay, see, nobody does, right? Come on, don't you really want to? Yeah, no, unfortunately you can't, right? So, the question I think that's been in my mind for basically like ever since I started thinking about blockchain scaling is like, can you take the spirit of how peer-to-peer torrent networks work, where you kind of split up the work and everyone only stores a little bit of everything, and combine that with the guarantees that blockchains provide. And data availability sampling is basically, I think, the closest that we have to an actual answer. So here is how dank sharding works. So you have a block, right? The things at the top here are Ethereum blocks. Ethereum blocks can have two types of transactions. They can have a regular transaction, same as today, or they can have a data transaction. A data transaction does everything that a regular transaction does, but also in addition, it contains a hash of a blob. And a blob is just like a bunch of data. So it contains the hash of a blob, and then you actually have the underlying blob that gets distributed through some kind of other system, right? Basically, you have a peer-to-peer network. Think of it just as, like, we're just going to break up the blob into tiny pieces, and we're going to publish the tiny pieces on BitTorrent. And then the Ethereum chain that contains regular transactions and that contains hashes of blobs, we're just going to push that around like a regular blockchain. Everyone downloads everything, right? So hashes of blocks distributed to everyone like a regular blockchain. Individual pieces of blobs go on BitTorrent. Now, if you're a node, you are going to verify the actual availability of the actual blobs in real time, but you're not going to like actually download the full blobs directly. Instead, you're going to check the blobs using a procedure called data availability sampling. Here's how data availability sampling works. You pick a bunch of random indices, right? So let's say the blob has 256 different pieces. Let's say you pick a random number from 1 to 256. 255. Okay, so we're going to check sample 255. Confirmed. Sample 255 is available. You pick a random number from 1 to 256. 25. Okay. It looks available. Okay, anyone else want to choose a random number from 1 to 256? Shout it out. Okay, not an integer, sorry. 69, okay. I like how random these numbers are. 69 is also available. Is anyone going to pick 42 now? Well, you got to pick 42, and then you got to pick 420 mod 256 as well. 42 is available, and then 164 is also available, so all good. So we checked in a bunch of positions, and they're all available. We just assume, okay, we checked it in enough places. we managed to download enough of the chunks, and so we're going to assume that the block is probably fine. This is data availability sampling. Now, it's a very simple procedure, right? But the reason why it works is actually pretty nuanced. Basically, one of the challenges here is that we need to actually ensure not just availability of most of the blob, but we need to ensure availability of the entire blob, right? So let's say, for example, I am evil. And the way that I'm going to be evil is I am going to create a block, and in that block, I am going to just hide one transaction, right? I'm going to publish all of the transactions except for one. Let's say, okay, some random number, transaction 142. I'm not going to publish that one, right? And that one I'm going to hide. Everything else is available. If we play this game, then almost all of the time, you're not going to check sample 142, right? And so almost all of the time, you're not going to catch the fact that what if that one transaction is the thing that's actually like sending someone $1 million, right? Like in a blockchain, a small amount of data can still have unboundedly large consequences. And so what we need is we need a system that doesn't just check that most of a block is available, but that all of a block is available. For this, we use erasure coding. Erasure coding is a pretty fancy piece of math that says that basically, if you have n pieces of data, you can expand those pieces into 2n pieces of data, where any n out of the 2n expanded set is enough to recover the original thing. One very simple version of erasure coding you can do in your head is 2 of n. So if we have 2 different pieces of data, then you can treat those two pieces of data as 2 points. Then you can make a line through those points, and you can just provide a bunch of other points on the line. Any 2 of those points on the line can recover the line, and once you recover the line, then like you check the standard coordinates, and you can recover the 2 original points, right? Erasure coding basically does this, except instead of lines, we use high-degree polynomials. So that is data availability sampling. And then there is extra mathematical stuff involving spooky weirdness called KZG commitments that basically let you prove that any one of these pieces is correct, even as you go through the entire erasure code, right? So it actually is like a very simple kind of highly specialized ZK snark, you can think of it, that basically proves that that any particular piece of data in the extension is actually in the hash, and if it's in the extension, it like is actually the correct extension, right? So once you have this, then what we actually do is we're not just going to take the blob, split it up into 256 pieces, and put that into a peer-to-peer network. Instead, take a blob, split it into 256 pieces, use erasure coding to expand that to 512 pieces, and then we add a KZG proof to each of the 512 pieces, and then we publish those 512 things out into the peer-to-peer network. And so now, when we play a game, you're going to pick 8 random numbers from 1 to 512, download those chunks and those proofs, check the proofs against the root, and then once you've checked that, then you know that like, well, okay, because you sampled randomly, and because enough other people are sampling with you that you could reconstruct the blob just from people's queries, you know that there is almost certainly enough, like more than 50% of the data has been published, right? Because if less than 50% of the data has been published, then like with extremely high probability, you would end up at least one of your sample requests will end up failing. So people understanding so far? Good. So now what we have is basically we've taken the problem of verifying that the entire blob is there. We turned it into a problem of checking that at least 50% of a thing is there, and then we solve that problem by doing random sample checks. So that's 1D sampling. 2D sampling is basically this kind of extension that says, well, we're going to not just do this extension within each blob, but we're also going to use the exact same erasure code extension algorithm to extend between blobs, right? And so now, even if you have 1,000 blobs of a lot of data, you could do the same sampling procedure in a two-dimensional way, but with only about 70 queries, you can sample and you can verify the availability of this entire grid that has like potentially like 1 million pieces in it. So that's the power of going two-dimensional. So with 50% of a row, you can recover the entire row, and with 50% of a column, you can recover the entire column. Now, so that basically is what full dank sharding is, right? It basically, it's a system where we add this new type of transaction, where in that new type of transaction, you have, you can put in a root of a blob, and then that blob is a bunch of data that gets uploaded through a separate peer-to-peer network, and then nodes, as they verify Ethereum blocks, they verify availability of the entire set of blobs in a block by doing this two-dimensional random sampling procedure, and in doing so, verify that enough of the data is there to recover the whole thing. Now, full dank sharding is complex, and full dank sharding is realistically many years away, and it really involves solving a bunch of unprecedented challenges in peer-to-peer networking and a whole bunch of other areas. What do we do before then, right? Like, what is a good sort of on-ramp that lets Ethereum applications have more and more scale over time, and actually, basically benefit from the safest, the most scalable version of the technology that actually is kind of safe in the short and the medium term. So the status quo is that we do not have that much data space, right? So if you want to calculate the theoretical maximum data space that Ethereum has right now, it's not super hard. You take the gas target, which is 15 million, divided by the cost of data, which is 16 per byte. 15 million divided by 16, 937,500. Divide that by the slot time, and I'm going to divide that by 12. And so divide by 3, 12,500, and then divide by 4, 78,125 per second, right? So about 78 kilobytes a second is what Ethereum theoretically has if literally all of Ethereum were to be used just for blobs, right? Now, unfortunately, Ethereum rollups still have to compete with huge numbers of other applications, right? Who here did a thing on Ethereum layer 1 in the past week? Just sent a transaction. Out of those who raised your hands, who was submitting a rollup block? Okay, so lots of you in the audience are using the Ethereum blockchain in a way that competes with providing space for layer 2, for layer 2s that could have put 10 times more transactions using that same gas than you could have. Fortunately, we have the first upgrade, 4844, which is going to make those two use cases not compete with each other, right? So what 4844 does is it basically says, we're going to have blob transactions, and those blob transactions will contain data, but for now, every node in the network has to download the entire contents of a blob. And so we're not actually making a technical scalability gain in the sense that we're not actually doing anything that technically opens up a possibility to store data that or transmit data that did not exist before, right? But what we are doing is we're making those things not compete with each other. We're making those separate spaces. We're laying the stage for making that possible with technology. And so with EIP 4844, blob applications applications that use blobs, particularly rollups, will actually be able to benefit from a pretty significant extra amount of data availability space. Now, it's still less than the current theoretical maximum, so it's going to be about 32 kilobytes a second, but it'll be quite a bit of rollup data space, and this will allow rollups to start adapting to this whole mechanism, and it'll kind of get the ball rolling here. Then you have intermediate stages, and then finally, we go to full dank sharding, where everyone actually uses full 2D random sampling. So proto-dank sharding, EIP 4844, nodes are still downloading all of the data, right? And the data blob space target right now, I believe 384 kilobytes per slot. I mean, obviously, it's still possible for that number to go up or down. Intermediate stages. So intermediate stages are what would happen pretty soon after EIP 4844. There are different ideas that are still being thrown around for this. This is still very early stuff where there are many different proposals, right? So one of them is to do basic forms of sampling. So don't go crazy on 2D, instead do 1D. Keep things fairly limited. So for example, you still do a mechanism where you would force every node to download, let's say, 1/16 of all the data. Be very conservative on the parameters. Split up more into different node types, right? So you allow heavier nodes to fully download everything and lighter nodes to sample. And if you combine some of these techniques, then you could allow increasing the target by potentially somewhere between 2x and 8x, right? And so if you're a lower powered node, you would sample. If you're a higher powered node, then like you would just like go and download 3 megabyte blobs every 12 seconds and you'd be fine with that. That's what intermediate stages would look like. Full danksharding, really a continuation of the intermediate stages, except you'd really do the 2D danksharding, and the desire is to have 16 megabytes of data space target every slot. And basically, once the sampling system is robust enough, you can start to have very few or even 0 nodes that individually download and store all of the data, right? Now, these stages are not kind of hard stages, and in the sense that like you can have a very smooth transition toward them. In fact, once EIP 4844 is done, the only hard fork that you need to get to full danksharding is just parameter changes. Like, just need to increase the amount of blobs that you're allowing. Everything except for that can just be done by plugging in different data verification backends, and it's totally okay for different clients to have different data verification backends, right? So everything after 4844 can entirely be done with like things that are not even soft forks. I'm not sure what kind of fork you could call it. It's like, I don't know, velvet fork, fluffy unicorn fork, something. So it's, basically we do AP 4844, and then after that, we just do a series of fluffy unicorn forks in the background where different nodes are going to be able to upgrade at different times and slowly make our way to having more and more scalability with more and more data space. And so that is the goal, right? So EIP 4844 is what all of this starts with, and it already puts up a significant amount of space that rollups can use and to publish your data on to ensure that that data actually is available. And so that anyone can download it, anyone can compute the current state, and if there's a mistake, like anyone can come in and catch it, and then over time start to increase that space as technology develops more and more, and over the next 5 to 10 years, slowly work over toward the Ethereum data space being a well, actually, like a pretty large space that's big enough for all of the activity that we want to do. So hope you guys understand, and hope you guys participate in making the Ethereum data availability future happen. So thank you.